Welcome, dear students. Today, myself, Dr. S.M. Thorat, Associate Professor, Sri Shivaji College of Arts, Commerce and Science, Akola, is here with an important aspect from Statistical Thermodynamics. That is, today we are going to discuss about a function that is partition function. So let's begin. The partition function is a dimensionless quantity. It summarizes in a convenient mathematical form as to how the energy of the system of molecule is partitioned among the molecules. The value of this partition function depends on the molar mass, the temperature, the molar volume, the internuclear distances, the molecular motion, and the intermolecular forces between the molecules. The partition function provides a bridge to link the microscopic properties of individual molecules, such as their discrete energy levels, moments of inertia, etc., with the macroscopic properties like entropy, heat capacity, etc., of a system containing a large number of molecules. So this important statistical function, that is the partition function, it is providing as a bridge to link the microscopic properties and macroscopic properties of the system that consists of a large number of molecules. Now let us see the expression for molecular partition function, which we are denoting by Q. For a microcanonical ensemble, the partition function, that is the molecular partition function Q, is given by equation 1. Q is equal to summation I is equal to 0 to I is equal to infinity Gi into exponential minus epsilon I by kT. So this is equation 1 that denotes the expression for molecular partition function, where in this equation Gi is the statistical weight factor and it is equal to the degree of degeneracy, that is the number of superimposed energy states. Its significance can be understood with the quantum theory. K is the Boltzmann constant in this equation and it is equal to the ratio of the gas constant R to the Avogadro's number Na. That is, the Boltzmann constant K is given by the equation R, that is the gas constant, divided by Na, that is the Avogadro's number. T is the temperature on the Kelvin scale. Epsilon I is the energy of the quantum state in excess of the lowest possible value. The summation is taken over all integral values of I from 0 to infinity. That means I is equal to 0 to I is equal to infinity, corresponding to all possible energy states of the molecule. Thus, Q is called as the molecular partition function. Now, if N0 is the number of molecules occupying the lowest energy level having degeneracy value G0, Ni is the number of molecules occupying a higher energy level with energy epsilon I above the lower energy level, then the Boltzmann distribution law can be written as Ni is equal to N0 divided by G0 into Gi exponential minus epsilon I by kT, that is equation number 2. Now the total number of molecules is the sum of all such terms as given by this particular equation. Thus, capital N is equal to summation, that is addition of N0 plus N1 plus N2 plus N3 plus and so on Ni, that can be written as equal to summation Ni. That means capital N can be written as equal to summation Ni. Now Ni, the value of Ni, substitute from equation number 2. So that is equal to N0 divided by G0 summation Gi exponential minus epsilon I by kT. So that can be written as equal to N0 divided by G0 and Q, because Q is the partition function, that is summation Gi exponential minus epsilon I by kT. Therefore, N0 by G0 can be written as equal to N divided by Q. Okay, that means if you have to write the value of N0 by G0, then N divided by Q, that is equation number 3. Now substituting this expression for N0 upon G0 into equation 2, that is in equation 2, for N0 divided by G0, you substitute N divided by Q. So we obtain equation 2. So this is our equation 2. Ni is equal to N0 divided by G0, Gi exponential of minus epsilon I by kT. This is our equation number 2. In equation number 2, we are substituting the value of N0 divided by G0 as N upon Q from equation 3. So our equation 2 becomes Ni divided by N, that is equal to Gi exponential minus epsilon I by Kt divided by this partition function, that is Q. So this is our equation number 4. What we have done? We have substituted the value of N0 divided by G0 from equation number 3 in equation number 2, and we have rearranged that this particular equation. We have got this particular equation 4. Equation 3 can be rewritten as N0 divided by N, that is again we are rearranging N0 divided by N, that is equal to G0 divided by Q, that is equal to 1 upon Q if G0 is equal to 1. Now since N0 divided by N is the mole fraction of the molecules occupying the ground state, hence the partition function is equal to the reciprocal of the mole fraction of the molecules in the ground state. Or we can write partition function Q is equal to 1 divided by N0 divided by N, that is equal to N divided by N0. Now since the value of N divided by N0 is greater than or equal to 1, hence the partition function Q is always either equal to 1 at absolute 0, N0 is equal to N, and only one energy level is accessible, or greater than 1. That means we can say that since the ratio N0 divided by, since the ratio N divided by N0 is always greater than or equal to 1, the value of partition function Q is also either equal to 1 or greater than 1. When we say that Q is either equal to 1, if the value of partition function is equal to 1, that means at absolute 0, N0 is equal to N, and only one energy level is possible, accessible, or the value of partition function can be greater than 1. At higher temperature, Q is much larger than unity because only a fewer molecules occupy the ground energy state. So equation 3 and 4 tell us that Q is a pure number and is a dimensionless quantity. Look at this equation number 3 and equation 4. From equation 3 and equation 4, we can say that the partition function Q is a pure number and it is a dimensionless quantity. The partition function simply describes the mode of distribution of molecules in the various energy levels. The partition function applies to a system of any physical state. The molecular partition function Q is calculated from the data obtained from quantum mechanics and spectroscopy. For monoatomic gas, there is no rotation and vibration. Even the electronic excitation at normal temperature is rare. Hence, that only contribution to the total energy in case of monoatomic gas is because of the translational motion of the monoatomic molecules. Now let us discuss separately the physical significance or importance of partition function. Okay, here we are representing the partition function by F. Qualitatively speaking, the partition function indicates how the particles are to be distributed among the various energy levels, various energy states or levels or cell. So partition function is a measure of available energy levels. Partition function is a quantity characteristic of every substance and also of a mixture of substances or a system. It reflects the diversity of energy states of the molecules of a system and relative probability of these states in comparison to the lowest energy level, which we denote by epsilon 0. So in other words, the relative population of any two quantum states P and Q is given by the ratio Np divided by Nq. So we can write Np is equal to N Gp e raised to the power minus epsilon P by Kt divided by the partition function F. Or we can write Nq is equal to N Gq e raised to the power minus epsilon Q by Kt divided by F. If you divide this Pp divided by Pq, then we can write Np divided by Nq. Here we are dividing Np divided by Nq, that is equal to Gp divided by Gq e raised to the power minus epsilon P by minus epsilon P minus epsilon Q divided by Kt. So what we have done, we have divided these two equations, Np divided by Nq. This N will get cancelled. Gp divided by Gq, here we have written, and e raised to the power minus epsilon P minus epsilon Q divided by Kt. This F will also get cancelled here. So here the P term denotes the probability at a particular level. The second form of distribution law gives the population in two different levels. Case 1. If these two states are degenerate, that is epsilon P is equal to epsilon Q, it follows that they are equally populated. And if epsilon P, one of the energy level is greater than epsilon Q, then NP is less than NQ, it follows that they are equally populated. As long as epsilon P minus epsilon Q is less than KT, the population will be of the same order of magnitude. If there are many low-lying states of energy substantially lower than KT, they all will be well populated relative to the ground state, that is epsilon 0. Now the next point that describes the significance of partition function. According to Maxwell-Boltzmann law, we can write Ni divided by N0 is equal to Gi divided by G0 into e raised to the power minus epsilon I by Kt. So this we are writing from MB distribution law, where Ni is the number of molecules in the energy state I, N0 is number of molecules in the energy state denoted by 0, and Gi and G0 they denote the degeneracy of energy level state, that is I and 0. When epsilon 0, that is the energy of the 0th level, is equal to 0, then we can write the degeneracy, that is G0 is equal to 1. Therefore, Ni is equal to N0 into Gi e raised to the power minus epsilon I by Kt. So here we are substituting when the value of epsilon 0 is equal to 0, then G0 is equal to 1. So the equation changes to Ni is equal to N0 into Gi e raised to the power minus epsilon I by Kt. Now if you take the summation of this above equation, we get summation Ni that is equal to N0 into summation Gi e raised to the power minus epsilon I by Kt. But we know from the expression of partition function that partition function f is equal to summation Gi e raised to the power minus epsilon I by Kt. Hence we can write summation Ni is equal to N0 into f. So for this summation Gi into e raised to the power minus epsilon by Kt, this is the expression for partition function. So the equation changes as summation Ni is equal to N0 into f. Since summation Ni is equal to n, and hence n is equal to N0 into f. Therefore, partition function f can also be written as n divided by N0 from this particular equation. So the equation states that partition function is the ratio of total number of molecules to the number of molecules in the 0th level. From this equation, we can also explain or describe the partition function as the ratio of total number of molecules to the number of molecules in the 0th level. Now, what about absolute zero? When absolute zero temperature condition is there, that is T is equal to 0 Kelvin or T is equal to 273 degrees centigrade, all the molecules tend to go in the 0th level. So, as T tends to 0, that is if the temperature tends to 0 Kelvin, N tends to N0, therefore the partition function F is equal to N divided by N0. So thus the value of partition function is unity. As n is tending to n0, that means both the value of n and n0 are equal. Hence the value of partition function is 1, that is unity. When both these two values become equal, the value of partition function is unity. This happens at absolute zero of temperature. But as the temperature rises, more and more molecules go to the higher energy levels and fewer molecules remain in the 0th level. Hence, according to equation, partition function f is equal to n divided by n0, the f will go on increasing as the molecules go to the higher energy level. So in other words, if the temperature is higher, larger is the value of the partition function. The next point that describes the significance or importance of partition function is partition function was introduced by Fowler and it is a dimensionless quantity. Its value depends on the molecular weight, molar volume, temperature, etc. The partition function provides a link between the microscopic properties of individual molecules and macroscopic properties of the system. It may be defined as the sum of the probability factors for the various energy levels or the ways in which the energy of the system is partitioned or distributed amongst the molecules constituting the system. So this can be an important definition of partition function. How can the partition function be defined? It can be defined as the sum of the probability factors for the various energy levels or the ways in which the energy of the system is partitioned amongst the molecules constituting the system. So in other words, the partition function may also be defined as the reciprocal of the mole fraction of the molecules occupying the ground state, that is epsilon 0 is equal to 0. It is also the ratio of total number of molecules n to the total number of molecules in the ground state. So these particular points describe the significance of partition function. Now, one of an important application of partition function is that in terms of partition function, we can write the equation for the thermodynamic functions. So we can utilize the partition function and distribution law to find the values of various thermodynamic functions as described below. Now suppose, for example, if you have to find out the equation for internal energy E. The internal energy E of a system of n molecules in excess of that at the absolute zero is given by the equation E is equal to n0 into epsilon 0 plus n1 into epsilon 1 plus n2 into epsilon 2 plus and so on plus ni epsilon I plus and so on. So this can be written as equal to summation ni epsilon I. Okay. Now, if you substitute the value of ni from Maxwell-Boltzmann law, the equation becomes E is equal to summation epsilon I, and substitute the value of ni from MB distribution law but in terms of partition function. So from MB law, ni can be written as n divided by f, that is the partition function, into e raised to the power minus epsilon I by kt. That means the equation can be written as E is equal to n divided by f. This you are taking outside the summation sign. So n divided by f, and inside the summation sign epsilon I into e raised to the power minus epsilon I by kt. Suppose if you write equation number 1. Okay. But we know that the partition function f can be written as summation e raised to the power minus epsilon I by kt. Hence, if you take the derivative of this, that is df by dt, then that can be written as 1 upon kt square summation epsilon I e raised to the power minus epsilon I by kt, or summation epsilon I e raised to the power minus epsilon by kt, that is equal to kt square into df by dt. Okay, so this was our equation number 1. E is equal to n divided by f summation epsilon I into e raised to the power minus epsilon I by kt. So what we have done, we have differentiated this particular equation. Okay, and we have got this particular equation, that is equation 2. So therefore, combining equation 1 and 2, okay, now in equation 1, you have to substitute the value of summation epsilon I into e raised to the power minus epsilon by kt from equation 2. Okay, so in equation 1, substitute the value of this term from equation number 2. Okay, the value is kt square into df by dt. So equation 1 becomes E is equal to n kt square divided by f into df by dt. Okay, so you are combining equation 1 and 2. That means you are substituting the value of this particular from equation number 2 and rearranging, the equation becomes in this way. Or you can write it as E is equal to n kt square d by dt of log of f, that is equation number 3. Okay, now for 1 mole, n may be substituted by capital N, that is the Avogadro's number. Therefore, equation 3 becomes E is equal to, instead of n, write Avogadro's number, that is n kt square d by dt of log of f, that is equation number 4. Now this can be rearranged as RT square d by dt of log of f, as the value of k, that is the Boltzmann constant, is equal to R divided by n. Okay, so here you, for k, you are writing R divided by n and rearrange this equation. So the equation for total energy E becomes as RT square d by dt of log of f. Expression 4 and 5, that is this particular equation 4 and this particular equation 5, will give the value of internal energy in terms of the partition function. Okay, so these two equations 4 and 5 are giving us the value of internal energy E, but in terms of partition function, that is F. The average of each molecule can be written as E is equal to kt square d by dt of log of f, that is equation number 6. Now we will take another example of thermodynamic function, that is entropy S. We have the entropy given by the equation S is equal to Nk log of F plus K beta into E. Now taking this B as 0. Now since beta is equal to 1 upon Kt, we can write the equation as S is equal to Nk log of F. If you substitute the value of beta as 1 upon Kt, okay, in this particular equation, put beta is equal to 1 upon Kt and you will get this particular, that is equation number 7. Now we have the equation number 3 from the previous point. The internal energy E can be expressed in terms of partition function, that is E is equal to nkt square d by dt of log of F. This we are writing from the earlier part which we have seen, internal energy E expressed in terms of partition function F. Now substituting the value of E from equation 3 in equation 7. So here in this equation 7, here this is the internal energy E. Substitute the value of internal energy E from equation 3 and rearranging the equation becomes S is equal to Nk log of F plus Nkt d by dt of log of F. So what we have done in equation 7, we have substituted the value of internal energy E from equation 3 which we have derived earlier. So we have got this particular equation 8 that gives the value of entropy in terms of the partition function. So S is the entropy and entropy can be expressed in terms of partition function according to equation number 8. Now let us shift to another thermodynamic function, that is the work function A. All of us know the work function A is given by E minus Ts. Now substituting the value of S from equation 7. So this is our equation 7. The value of entropy in terms of partition function S is equal to Nk log of F plus E upon T. So substituting the value of entropy S from this equation 7 and putting in this particular equation of work function. So A is equal to E minus Ts. Put the value of S from equation 7 and rearrange. The equation becomes A is equal to E minus T and put the value of entropy S. Rearranging that particular equation, that is solving this bracket, the equation becomes A is equal to minus Nkt log of F. That means from equation 9, we can see that there is a relation between the work function A in terms of the partition function. Now take another example of pressure P. We know that dA by dV at constant temperature T, that is equal to minus P. Okay, A here is the work function. So dA by dV, V is the volume at constant temperature T, can be written as equal to minus P. Now differentiating this particular equation 9 with respect to volume, because here we have dA by dV, that means you have to differentiate A with respect to volume. So you will get the this value of dA upon dV. So the equation of A is minus Nkt log of F. You have to differentiate this particular equation with respect to volume to get this particular fraction. So differentiating equation 9 with respect to volume at constant temperature, we have dA by dV at constant temperature T is equal to minus Nkt d by dV of log of F. Okay, so here we have differentiated equation 9 with respect to volume. So the left hand side is dA by dV at constant temperature T is equal to the right hand side is Nkt, all these are constant. So you don't have to take the differentiation of this, take the differentiation of log of F with respect to V, and that is d by dV of log of F but at constant temperature T. So therefore P is equal to Nkt d by dV of log of F at constant temperature T. Okay, so see this equation, pressure P can be written as dA by dV at constant temperature T, and the value of this left hand side is this particular equation. So we can represent the pressure P as P is equal to minus Nkt d by dV of log of F at constant temperature T. That means from equation 10 we can see that there is a relation between the pressure P and the partition function, that is F. That means you can express pressure P in terms of partition function F. Now let us see another thermodynamic quantity, that is heat content H, or we can call it as enthalpy. Since enthalpy or heat content H is given by the equation E plus PV. Now here you are going to substitute the value of E as well as V from the previous equation. Here we have the values of E, that is given by equation number 3, that is total internal energy expressed in terms of partition function, that is equation 3, and this is the value of P, that is the a pressure P expressed in terms of partition function F. So you have the values of internal energy E and P. You have to substitute these two values in this equation of heat content, that is enthalpy. H is equal to E. So put the value of E as nkt square d by dt of log of F. Here we have put plus V and substitute the value of P from equation 10. So that is nkt d by dv of log of F at constant temperature T. So what we have done in this particular equation, you have substituted the value of total internal energy E and P. Okay, and you have got this particular equation. Now you have to rearrange this equation. So H is equal to nkt. Take T inside this bracket. So T d by dt of log of F plus V d by dv of log of F at constant temperature T. That means here we have taken out nkt common. nkt common from here, nkt common from the second term, and that we have written outside the bracket. So inside the bracket will remain T into d by dt of log of F plus V d by dv of log of F at constant temperature T. So the equation becomes H is equal to nkt. This we can write as d by d log of T. Okay, that means derivative of log of F divided by derivative of log of T plus derivative of log of F divided by derivative of log of V. So we have rearranged this particular equation as equation number 11. As we know that 1 upon T into dt, that means derivative of log of T, and 1 upon V into dV, that means derivative of log of V. Okay. So using this particular derivative formula, that is derivative of log of T is 1 upon T into dt and derivative of log of V is 1 upon V into dV. So here we have rearranged this particular equation in this according to this formula. So we see that expression number 11 gives the relation between the heat content, that is H, and the partition function, that is F. Now take another example of thermodynamic function, that is free energy. We know that free energy is given by G is equal to H minus Ts. So substituting the value of H and S from equation 11 and 8. Okay, so this is the equation number 11 that gives the value of H, and this is equation number 8 giving us the value of entropy. So in this particular equation, that is 12, you have to substitute the value of H from equation 11 and substitute the value of entropy S from equation 8, which we have derived earlier. So substituting the value of entropy S and H from these two equations, that is 8 and 11 in equation 12. So if you substitute the value, you get G is equal to, now this is the value of H, that is nkt d log of F divided by d log of T plus d log of F divided by d log of V at constant temperature T, minus, okay, then substitute the value of entropy S, nk log of F plus nkt d by dt of log of F. So if you rearrange this particular equation, this is the rearrangement step, that is you're opening this bracket, introducing the minus sign here and opening this particular square bracket, the equation becomes this particular equation. So which can be written as, again nkt you take out common, so inside the bracket will remain d log of F divided by d log of V at constant temperature T minus log of F. So that is equation number 13. As we know that minus nkt square d by dt of log of F can be written as minus nkt d of log of F divided by d of log of T. That means derivative of log of F divided by derivative of log of T. So again here we have rearranged this particular equation and got equation number 13. So this expression, equation 13, is again giving us the value of free energy in terms of partition function, that is F. Now see the another thermodynamic property, that is the heat capacity C. We know that Cv, that is specific heat capacity at constant volume V, is given by the equation dE by dt at constant temperature at constant volume V. Okay, specific heat capacity at constant volume we represent by Cv, that is equal to dE by dt at constant volume V. Now we know the value of internal energy E from equation number 3. So you have to substitute the value of this internal energy in this particular equation and differentiate with respect to temperature. Okay. So in this particular equation of CV, substitute the value of this E, but you have to differentiate with respect to temperature. So differentiating equation 3 with respect to temperature, because here this is d by dt of E. The value of E is this. So you have to differentiate this value of E with respect to temperature, okay, at constant volume. So we get dE by dt at constant volume V, that is equal to d by dt of nkt square d by dt of log of f. Here what we are doing? We are differentiating this equation 3 with respect to temperature, because that is required in this equation, d by dt of E. So you differentiate E with respect to temperature, and therefore you get the value of dE by dt at constant temperature V, that is Cv, that is equal to, if you differentiate this particular bracket with respect to temperature, you will get Nk. Nk is constant, so you take outside the derivative, Nk into d by dt of T square d by dt of log of f at constant temperature T. So this is the expression, that is equation 14, that gives the relation between the specific heat capacity, that is Cv, in terms of the partition function F. So this is all about the relation between the partition function and various thermodynamic quantities. We have taken the example of 7 thermodynamic quantities which we can express in terms of the partition function F. So this was all about the partition function, its introduction, its significance, and how we can use the partition function to express all these thermodynamic quantities. Thank you.